In this lecture, we'll be discussing relative ages of rocks. Originally, the Earth was thought to be about 6,000 years old. The Earth, however, is about 4.6 billion years old. James Hutton is considered the father of geology because he theorized the principle of uniformitarianism. This means that current geological processes such as volcanism, erosion, mountain building, these all occurred in the past as well. This disproved that the Earth was 6,000 years old because mountain building and erosion takes more than 6,000 years. Relative age does not give you an exact date. It just tells you which rock is older than the other rocks. There are certain ways that we can determine this: law of superposition, law of cross-cutting relationships, unconformities, and index fossils. Sediments are originally deposited horizontally. This may change over time, but they're originally horizontal. This means that the oldest rocks are on the bottom, so this layer is oldest, this layer would be the youngest. Think of it like this. Let's say Monday you take your clothes off and you throw it in the hamper. Tuesday you take your clothes off and throw it in the hamper. Wednesday you take your clothes off, throw them in the hamper. Thursday you take your clothes off, throw them in the hamper. Friday you take your clothes off, throw them in the hamper. Where are the oldest clothes? Well, the oldest clothes are going to be on the bottom. Another clue that we can use is called an unconformity. An unconformity is a gap in the rock layer, which means there is a rock layer that's missing. There are three different types. A nonconformity forms when sedimentary rock form on top of igneous or metamorphic. We have angular unconformity. This is when the rocks are uplifted and eroded and deposited on again. And the last one is a disconformity. This is when sedimentary rocks form on top of other sedimentary rocks. This one's typically the hardest to identify. So here's the nonconformity. First we have an intrusion of magma. Rain and wind can cause erosion and erode away the existing rock layers. This ocean here will deposit them back on, and this is considered the nonconformity. This is usually identified in diagrams as a wavy line. An angular unconformity, I think, is the easiest to identify. Here the rocks are formed horizontally. For some reason they get uplifted and tilted, probably due to plate tectonics. The top gets eroded away, and more layers get deposited on top. So this is the easiest to identify because these rock layers are on an angle, and this is not. A disconformity is the hardest to identify. Here we have sedimentary rocks deposited horizontally. We have uplift and erosion. So you notice the purple layer is now missing. And now we get a new layer on top, so now the green layer is deposited. In diagrams, this is also shown as a wavy or wiggly line. Cross-cutting relationship says that if you have an intrusion or a fault, the intrusion or the fault is going to be younger than whatever it's cutting. So in this example, we've got an intrusion here, and it continues over here. We also have a fault. Take a moment and list them in order from the oldest to the youngest. Include layers A, B, C, D, the intrusion, and the fault. Okay, the oldest is going to be letter A, followed by B, followed by C. Next would be the intrusion. Now the intrusion is younger than layers A, B, and C because the intrusion cuts through A, B, and C. The intrusion is not younger than D because it does not cut through D. Next comes layer D, followed by our fault. The fault is the youngest because it cuts through all of the layers. Now we're going to look at fossils. Fossils can also give us a relative age of rocks. Fossils are 10,000 years or older imprints that gives us evidence of life. These could be the remains of the animals or traces of the animals. Paleontology is the study of fossils. Paleo is a root meaning old. Geologists use fossils to study the Earth's past and the history. We can learn things about when life began, when plants and animals first lived on land, when certain types of animals and organisms disappeared. We can also learn about specific things about the animal, such as how they lived, when they evolved, when they went extinct, and even in types of environments they lived in. Fossils are hard to make. Reasons, because we have dead animals, they'll die and decay, which makes them a little harder to fossilize. They can be eaten by scavengers, their bones can be scattered. Also, fungi and bacteria will also break down the animal. So in order to become a fossil, they have to be buried quickly. Also, it's important that they have hard parts such as bones and shells. It's possible to fossilize something without hard parts, but it's very rare. This is a picture I took of a plant fossil near Breezewood, PA. This plant will fossilize easily because they've got hard parts such as stems and bark. So these are the stems of the tree. There are different types of fossils. We can have the original remains. This can be created by mummification, which means dried, amber, tar seeps, and animals that get frozen. There's also petrification and trace fossils. Two examples of original remains. One, we have insects getting caught in amber, much like the Jurassic Park movie. However, the Jurassic Park movie is inaccurate in the fact that we cannot bring stuff back from the dead. Yes, we can get DNA from it, but we can't actually reproduce the animals. Another example would be frozen remains, like a woolly mammoth. In 1991, a frozen man who lived about 5,300 years ago was found frozen in a glacier in the Alps. So here's an example of a baby woolly mammoth that was recovered from a glacier. And here's a spider caught in amber. Amber is like sap that comes out of trees. So the animal will get stuck in it, the sap will come around it, and it stays there forever. Petrified remains are caused by water trickling down through the remains. The water will have dissolved quartz in it. As the water flows through the bones, it will dissolve the calcium in the bone and replace it with the quartz. This quartz is much harder, has a hardness of 7, so it will be rock-like. A good example is petrified wood. So here the wood has rotted away, and the water that trickled down through the wood replaced the wood with quartz. So now it's no longer a considered wood, it's now mostly quartz and other minerals. If you look closely enough, you can still see the rings, and you can still see some of the bark on the outside. This is an example of fossilized bacteria that I took out in Arizona. Trace fossils are evidence of the animal, but not the animal itself. So examples would be like footprints of where the animal might have walked, but again, it's not the animal itself. Or burrows. So if an animal were to dig a hole down in the ground, the imprint of the hole would be left behind. Here's an example of trace fossils. This is a picture I took on the outside bathroom in Valley Forge, Pennsylvania. These are wormholes. So this is where worms had once traveled through the dirt, and that imprint has been left behind. This is another example of a picture I took of wormholes. Here is a pair of sunglasses to give you size. This I took out in Zion National Park. This was used as a fence. So all of these lines here are wormholes. Here's another example. This was a picture I took outside the Grand Canyon. This is a dinosaur footprint and a baby dinosaur footprint. This is a pencil to give you scale. So here the dinosaurs were walking through a muddy lake, and that footprint has been left behind. To give you scale, my friend and I are standing in the footprints. Organisms are constantly changing and evolving or becoming extinct. Some species over time will evolve very slowly, some will do very rapidly. An example, cockroaches have been around for about 300 million years. They haven't changed a whole lot in those 300 million years. On the other hand, take a virus or a common cold. The cold will actually evolve every year. This is why you have to get a different flu shot every single year, because it changes every single year. Index fossils are species that have existed for a relatively short period of time. They have to be abundant and they have to be widespread geographically. if they were present for a very long time, such as cockroaches, they're not going to be very useful. If you find a fossilized cockroach, it's not going to be able to tell you when it formed because cockroaches have been around for a long time. So they have to live a short period of time. They have to be abundant, so there has to be a lot of them so they're easy to find. And they have to be widespread geographically, which means they have to have a large area in which they used to live. If a geologist finds an index fossil in a rock layer, this gives the geologist an idea of about how old the rock is. Fossils can also be used to determine what type of an environment the area was like. For example, in Antarctica we find tropical plant fossils, so Antarctica used to be a tropical rainforest. Another example, brachiopods, which live in very shallow seas, are found in the Midwest United States. So this tells us that the middle of the United States used to be a shallow sea. These are some examples of common index fossils. First, we have a trilobite. This is Pennsylvania's state fossil. This was a little critter that walked on the bottom of the ocean floor. They were very abundant and short-lived. Next here we have a brachiopod. This was, if you would think of it like a clam, this used to live in the shallow sea. And an ammonite. This also is an ocean-dwelling animal. This diagram shows common index fossils that we use to date rocks. For example, this trilobite lived in the Cambrian period. Another example is this ammonite used to live in the Jurassic time period. Earlier in the lecture, I talked about disconformities being very hard to identify. One way we can identify disconformities is by looking at index fossils. So here we have two geologic columns, both having sedimentary rocks. And they're also separated by many miles. In this column, we have index fossils 1, 2, 3, 4, 5, 6. And they're all in sequential order. Over in this column, we've got 3, 4, 6, 7, 8. So we're missing index fossil number 5. This would be a disconformity and it's represented by the squiggly line. This concludes our lecture on relative dating.